Let us begin, cabbages. A prime number. All of you remember what a prime number is. What is a prime number?
A number that's only divisible by 1.
Right. A prime number has two factors. 1 and itself. There is no predictability to prime numbers. They are completely random. I can't remember what the biggest one is, but it's well into the billions that they have discovered. They are very powerful because they exist no matter what your language is. Even if you say you are Klingon, which isn't real, and you say this is 1, a kreplach, it is still 1. It is still a number, no matter what you call it. There is no other way to count. Prime numbers exist in every system. So, eventually, when the aliens do come to talk to us, it will be based on math. Prime numbers, two factors, 1 and itself, which means there are only... No, I don't want to say that. A prime number is two factors, 1 in itself. Oh, I should have written that over here because that gets messy. I'm going to write it over here where it won't be as messy. Prime number is a number with two factors. 1 and itself. Alrighty? Now, every other number is a composite number. There are infinitely more composite numbers than there are prime numbers, even though there's technically an infinity of prime numbers as well, because infinity is the end, which you never get to. But that is number theory that you don't need to care about. What I do need you to care about is there is one very special prime number. What is it? It is the Optimus prime of prime numbers. What is it? No, 1 is not a prime number because 1 only has one factor, 1. 2. Why? Why is 2 the most powerful prime number? Because it is the only even prime number. Every other prime number is odd because every other number other than 2 is divisible by 2. Okay? Very important. Now, before I go further, I am going to slide way over here to remind you guys of a few things. I have found out recently, well, not recently, over the last few years, that you guys no longer are forced to multiply or forced to memorize your times tables. Many of you feel you have memorized your times tables. You haven't really. You know how to multiply. So when I ask you what 12 times 7 is, every one of you can take a half second and go, 84. But most of you cannot say 84 as the N of 12 times 7 leaves my mouth. If you say to me, what's 12 times 6? As soon as I hear 6, I already know you're saying 6, and I've already said it's 72. That's memorizing. You guys don't have that ability, many of you. Don't worry about it. It doesn't matter. However, you were taught all these crazy tricks to learn multiplying, which is infinitely more difficult than actually learning the 12 by 12 grid, which is all it was. But you guys have all your count on the fingers, 9 times 7 is 63. You have all of this. You have one for almost every number. Except you mix them up then and you don't use the right trick at the right time, which is fine. However, I found out recently that in our zeal to give you all these shortcuts to learn to multiply, nobody bothered telling you how to learn to divide. Because when you know your times tables, like actually know your times tables, then division is super easy. You always know what the factors of every number is because you know how to multiply. Since many of you were taught to multiply by using silly tricks, you should have been taught to divide by using silly tricks. But every year I teach this class, I find that you were not taught the tricks for division. You were only taught them for multiplication, which means when we are doing this and you have to divide, you stink at it. It's not your fault. So I'm going to do a couple of those tricks right now. How do you know you can divide a number by 3? Do any of you know that? Tavleen? Yes. To divide by 3, if the digits add to a number that divides by 3, you can divide the whole number by 3. For example, 321. That divides by 3 because 3 plus 2 plus 1 equals 6, and 6 will divide by 3. So 321 divides by 3. Everybody cool? Divide by 2 is obviously if it's even. So the next one that I know of is divide by 5 if it ends in 0 or 5. Divide by 6. If you can divide by 2 and 3, you can divide by 6. Okay? I don't know if there's one for 7. I don't know if there's one for 8. And there is one for 9, but I can't remember what it is. It's something to do with adding up all the digits again. Okay? If you add it up and it equals 9?
Yeah, like, you know how like thousands of stuff to that 3.
Okay, thank you. So divide by 9 is when the digits add to 9. Okay, so there's a little bit of help for this unit. Okay? It's recorded if you didn't write it down. Don't worry about it. You can get them later. So next thing we're going to do is what you did in grade 4 or grade 5 is you made factor trees. Now, as I said before, when you made these, this was the end. Your teacher gave you 100 of these, you did them because you did, and then it ended, and you moved on to the next topic without ever talking about what these things were useful for. We're going to use them right now. Of course, you did use them almost immediately because you use factor trees to find lowest common denominator when you're adding fractions, even though you don't think you do. So most of you will have learned this move, 9 times 6. And then you would carry on, 3 and 3, 2 and 3. And when you get to prime numbers, the branch ends at a prime. Okay? And that is about where grade 4 or 5, whenever you did factor trees, ended. Right? We're going to go a step further. Once you have that, you write it out. 2 times 3 cubed. Because there's 3 2s, 3 3s there, and 1 2. Yes? This is what we call a product of primes. And it is an extremely powerful and useful math expression. Okay? Everybody cool? Now, there is more than one way to make a factor tree. Some of you were taught to make them horizontally. Same thing. The way I like to do a factor tree is not a tree at all. I like to do this, and you are welcome to steal this from me. 54 divides by 2, because I know 2 is a prime number. That gets me 27. 27 divides by 3, because I know 3 is a prime number. That gets me 9. 3 and 3. And then all my primes live out here. I do not care what you do. I do not care if you have even a third or a fourth or a 27th way of factoring. Do what works for you. I've given you 2. Okay? Now, the problem that kids always have is when I start a factor tree, they're like, but I didn't use 9 and 6, Mr. Myers. It doesn't matter. As long as every branch goes to a factor, if you continue to prime numbers, you will get the same answer. Okay? Okay. So now you're going to do 162 in whatever method you see fit. And you are going to tell me the product of primes that is 162. Go. Bong, bong. Are you done? Okay. Matt,
Can I ask you a question?
please do.
Oh, right now? Okay. Well, I did like the thing you did there with
The steps?
Yeah, the stepping.
Yeah.
The stairs. So, but I was wondering, could you go, since it starts at 162, could you just go straight away to divided by 9?
But
That's not-
then you're going to end up with 162 divided by 9 is going to get you 18, yeah? And then you're going to do 18 divided by 9 again, too. Now, the only problem with that is these aren't primes.
Yeah, so,
So you got to prime them as well.
wait.
So you
okay.
just, then you would mix it up. And you can use a hybrid of trees and steps.
Because I did that originally, then I just did, like, divide by 2, then divide by 3, then divide
Yep.
by 3, then, yeah. Okay.
Again, that's what I was just saying. Whatever method you use. But the point is you need to get it down to prime numbers. Okay?
Yeah.
Everybody cool? Everybody got that? Everybody's good to go. Now, we're going to leave them there because we're going to come back to them in a minute. Okay? So, first thing we're going to talk about is GCF, greatest common factor. What is a factor? Pardon? Even simpler. What are factors? Numbers that do what? Pardon? They make a product, right? So the factors are anything that you multiply together to make a product. Anything. Okay? 27 and 4. Those are factors. They're not prime numbers. They happen to be factors, though, once I multiply them. Everybody good? Okay. So that's what a factor is. What does common mean? Shared. Excellent. What does greatest mean? Biggest. So right here I am looking for the biggest factor that is shared between some numbers. Yes? The factors, what are the numbers that we are looking to find? We are looking, or what are the numbers for whom factors we seek? Those are the products. Yes? So a greatest common factor is the single largest number which is a factor of a group of products. Okay? So for it to be a group of products, how much does that mean I have at least? How many products must I be searching? At least 2. Okay? Now, we are going to take what you learned in grade 5 and show you that it has a use. A greatest common factor, GCF, and I'm going to remind you that that is abbreviated as GCF. A GCF can be found using prime factorization by counting the prime factors that appear for all your products. And we're going to show you how to do that in a minute. I just want to, that's what you do. Everybody cool? You haven't seen it work yet, but that's what you do. You get a list of products, you get a second list of products, and you count everything that is in both lists. The next thing we have is the lowest common multiple, which is LCM. You may have never seen that, but you have used this. This is what you use to find the LCD when adding fractions. That is what the LCM is. Okay? And it differs from a GCF because the lowest common multiple is the smallest, not the largest, the smallest product of which your group of numbers is a factor. What? What do you mean? In regular English, GCFs are divided out of your group. So GCFs are smaller. LCMs, I don't want to make the arrow that big. LCMs are multiplied out from your group. So they are bigger. Everybody cool? All right. Now I'm going to tell you in a sentence how we do that, and then we're actually going to do it for 54 and 162, okay? So an LCM can be found using prime factorization by counting every factor once. Please highlight once. And then in brackets, no repeats. And we're going to put that into practice right now. So the first thing we're going to do is we're going to GCF 54 and 162. We have already done the work here. We already know what the prime factorizations are, don't we? What is 54 as a prime factorization? 2 times 3 cubed. Yes? That's 54. Because 2 times 3 cubed is 27. 2 times 27 is 54. Everyone is good, yeah? Okay. 162 is 2 times 3 to the 4th, yes? All right. So, according to your notes, what do I have to do for GCF? Count the prime factors that appear for all of your products. Is there a 2 in all of our products? Yes. So we count the 2. Is there a 3 in all of our products? Yes, so we count the 3. How many 3s are in all of my products? 3 or 4? 3. Because this guy can cover all of them, but this 3 cannot cover him. Understand? So it is 2 times 3 cubed, which is 54. Does that make sense? Is 54 a factor of 54? Yes, because 1 times 54 is 54. Good? Is 54 a factor of 162? Yes, because 54 times 3 is 162. Everybody good? All right. So now let us move on, cabbages, to 2 times 3 cubed and 2 times 3 to the 4th. If I'm going to LCM that, I need to count every factor once with no repeats. So, how many 2's must I count? One of them, because I don't repeat. 2. How many 3's must I count? This is where it gets tricky. You have to count everything once with no repeats. So how many 3's will cover all the 3's? This guy has 3 3's. This guy has 4 3's. Which of those do I count to count all of them once? 4 or 3? 4. Because I have to, once I count this guy, that covers this guy. I don't want to repeat him. Once I count this guy, that covers this guy. I don't want to repeat him. Once I count this guy, that covers this guy. I don't want to repeat him. So I don't need to do them. But I do need to get this guy. So that is 3 to the 4th. Which, surprisingly, is 162. Does that make sense? Is 162 a multiple of 162? Yes, because 162 times 1 is 162. Is it a multiple of 54? Yes, because 54 times 3 is 162. Now, the next thing you have to notice is the GCF was the same or lower than the two products. The LCM was the same or bigger. Got it? Because multiples go up, factors go down. We find factors by dividing. We find multiples by multiplying. Guda? Great. Turn the page over, and you have 4 of them to practice. And that is all you are going to do right now. I'm not even... 36. Again, it doesn't matter how you break it down. I'm going to break it down in a way that I bet none of you did. You use 12 and 3? Nice. 2 squared times 3 squared, yes? 120. 10 and 12. 2 and 5. 2 and 4. 2 and 2. 2 and... I jumped ahead of myself. 2 and 6. 2 and 3 to get 2 cubed times 3 times 5. Now, GCF, everything that's in both. Is there 2's in both? Yes. How many? 2. 2 squared. Is there 3's in both? How many? 1 times 3 to the 1. Is there a 5 in both? No. So the greatest common factor is 12. Okay? Now, LCM. 2 cubed times 3 squared. 2 cubed times 3 times 5. Now, count everything once with no repeats. How many 2's will cover all the 2's once? 3 of them. 2 cubed. How many 3's will cover all the 3's once? 2 of them. Do I count the 5? Yes, because I need to count everything once. So that is 8 times 9 times 5, which is 360. Okay? Everybody good? All right. Carry on with the next 3. I'm just going to do them. You can look up here periodically, make sure you're doing it right, or watch the video later. I don't need to talk about it more because there's nothing more to it. The only way to get better at it is to practice it. Yep. Please check and make sure you've been working right up to wherever you are.
Wait, can you scroll it up a little bit so I can see? 6 times 8 is 72.
Where do you see 6 times 8?
Well, 2 to the power of 3
Is 8.
times.
3 to the power of 2, dude. Don't tell me that's 6.
Oh,
3 to the power of 2.
my bad. I thought 2 to the.
It's okay, I understand.
3 to the power.
Everybody does it, Max. If I had a nickel for every time somebody told me 7 squared was 14, I would be the richest man in the world. Exponents, for some reason, do that to everyone. All right, now, I need you guys to, you can go back and finish this in a minute, but I need you to understand something. What if the group is bigger than 2? Does anything change? Like, for example, I add a third number here, 81. No, you would just have a third stack here, and you would count all 3. Does everyone understand that? Okay. Now again, this seems like the end of the road, yes? But it is not. It is the very, very beginning of a long road of factoring and a long road of multiples. Okay? Is everybody cool with it? All right. So turn the page over, please. You guys should be looking at a page that says roots in King Things Extortion font. Your page, you have some work on page 100 of your blue book. That is homework. Or today's class if we get done. Page 100 from your blue book. Which in your blue book is titled page 140 and page 147. And the answers are right there upside down at the bottom of the page. That's your first bit of homework. Or work. Now we're going to move on to this. Here is a rectangle. How do I find the area of a rectangle? Right. Rectangle area equals length times width. Yes? We all know that. 1, 2, 3, 1, 2, area is 6, yeah? What if it's a square? It's still length times width, because square is just a rectangle, isn't it? Except now, because it's a square, L equals W. So do I need 2 letters? No, I give it 1 letter, S. It's still, area is still length times width, but since length and width are the same, it's S times S. Math guys are lazy, so they say S squared. That's where the term comes from. That's why an exponent of 2 gets the nickname squared, because it's how we make a square. W, L, but they're the same as S and S. Okay? Now, if you are provided with the area of a square, how do you determine the length of each side? Square root. That's how we get that name. Because you can't have a square without starting somewhere. And a root is where you start. So if you are provided with the area, if area equals side squared, then side must equal the opposite, which is square root of area. Right? So if my square is 4, 1, 2, 3, 4, the sides must be the square root of 4, which is 2. This is the symbol we care about, which up until now you have called the square root symbol. And you have used it only, almost only, in what? Pythagoras, yeah. Trig, right? Up until now. Okay? You are going to get very friendly with this symbol for the next 2 or 3 years. It is not only for Pythagoras, which is another failing of our math system. They taught you Pythagoras in grade 6, grade 7, maybe, and you were like, okay, I got it. I know what a square root's for. Yes, in one case. Square roots have infinitely more uses. So let's fix this up. This symbol is asking you, this symbol, first of all, let's name it. It's called the radical symbol because it's radical. Not really. It's just what we call it. This symbol is asking you to find 2 equal factors. Okay? So, square root of x means I need factors of x that are equal. 2 of them. Got it? And up until now, you have only been able to do this with your calculator. Correct? Up until now, if I ask you, well, unless you've got it memorized, because the square root of 16 is 4. But if you get a weird number, up until now, you have needed to go to your calculator. For example, what is the square root of 31? Huh? 5.6. Is it? Of course. It's an irrational number, isn't it? Why did you say 5.6? Because you rounded it off. On your calculator right now, do 5.6 squared and tell me what you get. Is 31.36 31? No. Your calculator is lying to you. It is giving you an estimate. From now on, you will almost never be asked to find that estimate. Okay? Of course it's a prime number. That's why I chose it, so everyone would go crazy. Okay? Is this better for you, Tavleen? What's the square root of 21? I know. I'm aware. That's why I chose 21.
Okay, guys.
You have been shown what I'm about to do.
Yeah.
Tomorrow, not today. Monday. All right. How do I find the volume of a rectangle? Length times width times height or depth, yes? Why are there 3 measurements of a prism? Because there's 3 dimensions. So volume equals LWH, right? What if it's a cube? Well, if it's a cube, what do we know about L, W, and H? They're all equal. So we can give them how many variables? 1. S. So the volume of a cube is still LWH, but LWH are now all the same. Math guys are lazy and they're not a snake, so it's S cubed. Really, guys, not a snake? Nothing? That's why the third power gets the nickname cubed, because it's how we make a cube. Okay? Now, if you are provided with the volume of a cube, how can you determine the length of the sides? Well, if it was a square, we needed 2 equal factors. So if it's a cube, I must need how many? 3 equal factors. So you find the cube root, which is 3 equal factors. Now this is the symbol for a cube root, and it is asking you to find 3 factors of x if it is cube root x. Now please look at this and this. What is the difference? That little tiny 3. And you can see my next note will explain that little tiny 3. The small 3 is called the index. Please highlight, underline, Mrs. Bad Crumble, happy cloud around it. Stars, I don't care. Know that word, because I'm going to use it ad nauseum, which means until you are sick of hearing it. And I will never call it that little number in front of a radical sign, because that's not its name. Just like I don't call this good-looking cat right here Jehoshaphat, because his name is Max. I will be saying the word index, so you better know what it is I am speaking, of what it is I am speaking. Okay? It tells you the group size of factors. So, if there's no number, I need 2. If there's a 3, I need 3 factors. If there's a 4, I need 4 factors. If it's anything else, I need that many factors. Okay? Everybody good? Great. A perfect square or a perfect cube, perfect ones, perfect square or perfect cube is any rational number which has 2 or 3 rational equal factors. Now, your guys' page should end there, yes? Mine doesn't. I wanted you to have a bit of blank space here, so I'm just going to erase this right here, and then I'm going to write a little bit more, because you guys should have a blank there. It's like whiteout. Okay. Here is what I am speaking, okay? The square root of 64 is what? What are the 2 factors of 64 that multiply together to make 64? 8. You're all good at that. No problem, right? Know it in your head. Okay. 64 is a perfect square because it has this. 64 is also a natural number, isn't it? Because when we count, we will hit 64, right? The Beatles hit it in one of my favorite songs. That is fine. Now, if I give you this, 12.25, that does not look like a perfect square because you don't know, because it's not one of the ones you're used to. But go to your calculator and tell me the square root of 12.25. 3.5. Is 3.5 rational? Yes, because it's 3.5. Are they equal? Is 3.5 equal to 3.5 if I multiply them? Are they the same? So does that make 12.25 a perfect square? Yes, even though it's got a decimal. Got it? As long as your square root is rational, you have a perfect square. Cool? Okay. What if it was a perfect cube? How do you find that? On your calculator, most of you will have a cube root button with a little X or a blank there. And you use that button just like a square root button. Use it exactly the same. So what is this cube root of 64? 4. Okay. Everybody good? Yeah. Oui. All right, because I know some of you have a French quiz, so we'll practice our French today. Parce que vous écrivez un examen en français. Max, stop shaking your head.
I didn't shake my head.
You wanted to. You're just being nice to me. All right. Now, when you turn your page over, you will see the sentence that I whited out. Yours is written there. Square and cube roots, up until now, have been the goal. Right? Oh, Pythagoras. 3 squared, 4 squared, 5 squared, square root 25. 5, got it! Gold star. I get an A in math. Right? That was your grade 7. Don't tell me it wasn't. I know it was. They taught you one step and you thought you were geniuses. It's okay. It's how we work in Canada. We don't like you to think that it's possible that you might not be awesome. Yet. yet. So, you can read that sentence right there. I cannot stress how important from now on memorizing these two things are. It's kind of as important, and it will make your future math as easy as if you actually had your times tables memorized now. Okay? It gets you to the point so you don't have to waste any of your RAM working out easy stuff, so you can concentrate on the stuff that's actually difficult. So we're going to list them. Roots on top, 1, 2, 3, 4. Squares on the bottom, 1, 4, 9, 16, and so on. We won't get to using these today. Well, that's not true. We will. 8, 64, 9, 81, 10, 100. 11, 121, 12, 144, 13, 169, 14, 196, 15, 225, 16, 256, 17, 289, 18, 324, 19, 361, 20. Oops, I want to make a fraction. 20, 400. I cannot stress this enough. And of course, you recognize the pattern. Add 3, add 5, add 7, add 9. So this, I added 19. So what's the next perfect square? All right, sorry, not 19, 39. So what's the next perfect square? I add 3, 5, 7, 9, 11. So I'm going up by I added 3, then I added 5, then I added 7, then I added 9, then I added 11. So this one I added 39. So what do I add here? 41. So 441 would be 21. Then I would add 43. So 22 would be 484. Okay? That goes on forever. But if you know up to 20, you're in good shape. The tens, 1, not the tens. The cubes, 1, 1, 2, 8, 327, 464, 5, 125, 6, 216, 7, 343, 8, 512, 9, 729, and 10, 1000. Will I ever test you on it? No, because the world gets mad at me if I test your memory. Because it's not fair, because some kids have better memories than others, and they shouldn't be made to feel special. Not true. You play soccer, right?
Yeah.
At a high level, right?
Yeah.
Do you get rewarded for playing at that high level? Are you better than some of the kids on your team?
Yeah.
Do you play more than they do?
Yeah.
Okay. So you should be rewarded for it, right? Because you have a talent of playing soccer. If you have a talent for having a good memory, shouldn't you be rewarded for it? Sure. Can your memory be improved upon through exercise and practice? Yes. So if you choose not to improve upon your memory through exercise and practice, should you not be punished for it? Yes. But we don't do that in Canada because memorization's evil. Okay. Now we're going to use this. And again, some of you may be beyond this. That's okay. This is actually very, very useful. But again, it's going to seem like it's the end. Square root of 72. Look on your list. Does 72 have a square root? No, but 64 does, and 81 does, yes? So the square root of 72 must be between the square root of 64 and the square root of 81, correct? What is the square root of 64? 8. What is the square root of 81? 9. So this guy's square root must be in the middle, yes? Where is 72? Is it closer to 64 or closer to 81? It's 12 away from 64, and it's 9 away from 81.
81.
It's close to 81 by a little bit, yes? So it must be a little bit closer to 81 from 8.5, yes? So what if we said 8.6? Everybody cool? Now with your calculator, you don't need to do this. Square root 72. 8.48. Are we happy? Oh, I lie. It's only 8 away from 64. It should have been just that side. I added wrong. So it should have been just a little bit shy of 8.5. So we would have said 8.4. Everybody cool? Now, how does this have use for us? What's easier? Okay. Are you ready for this? Tell me how to walk from the Louvre in Paris to the Eiffel Tower. Go. Can any of you do that right now? Give me those directions. Why? Because you don't know where you're going, do you? Excellent. Now, tell me the square root of 73 plus the square root of 85 minus the square root of 17. Wait, don't really. What would you do to do that? You would punch that all into your calculator, right? That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 button pushes plus an equal sign. 12 button pushes. How many of you have hit a wrong button ever on your calculator? All of you. Now, let's take a second and think about this. I know the square root of 73 is about 8.5, don't I? Right? Square root of 85 is a little more than 9, isn't it? So I know that's about 9, yeah? Square root of 17 is a little more than what? 16, which would be 4. 8.5, 9, and 4 is 21.5, right? Now, you now go to your calculator, you punch it in, and you get 312. Did you punch your calculator in right? No. Because you did that estimate, you knew approximately where you were going. Kind of like how the hypotenuse can't be 5.6 when one of the legs is 8.9. Right? Right. So now you guys are going to do exactly what I just did with all of these. What's 180 between? 169, which is 13, and 196, which is 14. Where? Closer to 13 or closer to 14? 13. So 13.5. So I would say, what? What's your guess? 13.4. Let's check. Square root, 180. Holy crap. 13.4. Useful? Yes. So you have an idea of where you are going before you ever try it. So when your calculator gives you a gobbledygook answer, you don't do this. The calculator said so. Okay? 300. What's it between?
289 and 320.
17 and 18, which is 289 and 324. Which am I closer to? 17, right? Is it real close to half, or is it significantly closer to 17?
Like, big.
It's significantly. So I would say 17.3. Would I be right? Square root, 300.
Yeah.
Oops, I did square root of 30. Because my calculator, or my pen doesn't always make connection. Oh my good God! And it's not like I have these memorized, because I don't. because I don't care about memorizing them. Now, what is different here? Cube root. So what's 45 between? We go to the other list. 27 and 64. Which is it closer to? It's almost exactly in the middle, isn't it? It's almost 20 away from 47, almost 20 away from that. So what's our guess? 3.5. Now let's practice with our calculator. Cube root. If you have this fancy calculator, how many people have the fancy calculator? Then you got to push math. And there is your cube root, number 4. Okay, if you have a regular calculator, somewhere on your calculator, there's a cube root button. Just look for it. 4, cube root 45. 3.55. Cool in the gang? Can everybody find it? Great. Yes. Ah, you have one of the pain in the ass calculators. So your little exponent button, see how it's got an X for an index? You push your index first. 3, that button, 45.
Okay.
So you've got to tell it its index. Everybody good? And lastly, these two. 405 is between what and what? 343, which is 7, and 512, which is 8. Which am I closer to? Again, what am I closer to? The 7, right? So 7.3. 176 is 125 and 216. 50 away from that. 40 away from that. Slightly closer to 216. 5.6. Is everybody good? Yes? Huh? Can I still assign? Not yet. Turn.
Oh yeah, you did.
Well, yeah, I gave you that. Yeah.
Page 100.
Yeah. I'm about to shut up, though. I'm going to be done right here. You guys should have. Where is it? Not that. Not that. Damn it. Not that. Damn it. Not that. Damn it. Not that. Damn it. Ah, that's a test. Okay. You guys, I don't have. Oh, wait. I might have it over here. Is it that? Nope. Is it that? Nope. Is it that? Nope. Is it that? Oh. Oh, it's that. Okay. So I've already given you something to do. Then you are going to do in your book, page 103. But wait a moment. There's a couple of these I want to show you before we go any further. Okay, I'm going to show you a few of them. C. What is that radical sign covering? Everything, right? So that is the square root of 9 over the square root of 100. What's the square root of 9? 3. What's the square root of 100? 10. That's how you do those. Okay? Now please look. All I am asking you to do is tell me if it works. If it doesn't work, you leave it as irrational. Everybody cool? Okay. Next one I want to look at. This one. 0.25. That is a bunch of different things, isn't it? It's 25 over 100, yes? So it would be the square root of that. It's also 1/4. So it could be the square root of that. Right? Same thing. And a because I want you to avoid your calculator as much as you can for this, right? This one, 27,000 on your guys' page 104. That is really the cubed root of 27 times 1,000, isn't it? Does 27 have a cube root? What is it? 3. Does 1,000 have a cube root? What is it? 10. So this is really 3 times 10, yes? Because this is really the square root of 27 times the square root of 1,000. Everybody cool? Okay? Remember, I want you to try not to use your calculator for page 103 and 104. Because all you're doing is either telling me the answer or writing irrational. What do I mean by that? Let me give you an example. If I told you to tell me the square root of 14, is that on your perfect square list? Nope. So that, all you would write is irrational. I don't need a value. Okay? But if I gave you something like this, square root of 12.25, you may want it, that one I want you to think about. Because you know that's a perfect square, don't you? Because that is 1,225 over 10,000, isn't it? Right? Right? Which would mean the square root of that. Now there you might need to go to your calculator because that's a big number. You understand what I'm saying? Use your judgment. If you have to use your calculator, go ahead and use your calculator. But try to avoid it. Because this is, of course, 35 over 10, right? Which is 3.5, which we knew was, actually that's 12.5 over, 1,225 over 100, which we knew was the answer anyway, right? Go. And that's your work for the weekend.